Well, good morning, everyone. Hopefully things are going okay for y'all. Um, Looks like we don't have too many folks on stream yet, but hopefully folks will show up as we continue through the stream this morning. So hopefully the exam went well. I haven't had a chance to get in and grade it yet. This is my two other courses required a ton of attention as well, so I haven't gotten into grading that yet. But soon I'll get to that. I'm hoping to get to that by the end of the week, and that sort of stuff. So you'll have some sense. Hopefully that went well. If folks have questions or concerns about how the exam went, feel free to either, if it's for public consumption, post in the discussion boards, or feel free to email me if it's more of a private concern or something like that. Hopefully folks are getting along with this stuff. If not, well, just like I said, just let me know, and hopefully we'll be able to work some things out here. So, I think what I'll do to start out here is I will talk a little bit about the lecture notes that I posted this week, and then we'll open it up, and it's open up for questions now. Ask any questions away that you have there, but I'm going to give sort of an overview and an introduction to the material that was hopefully been covered by the set of 3 lecture notes that were posted on Monday for you to have a look at. And if there's homework questions and stuff like that, feel free to ask those as well. So the floor is open. Ask away. So and also just let me know you're here too. We have a few viewers on, but not too many. So glad to say hi. Hopefully folks are getting through this whole social distancing stuff and state shutdown okay. My thoughts go out to you. Hopefully everything's going all right with y'all. I know it's an unusual time, but we'll do our best to get through it as best we can. So let's talk a little bit about the physics of the idea of work and energy. So the first thing that we talked about, or that we will be starting talking about then this past Monday, is the idea of work in physics. So let's talk about that and look at the definition for that. It's a little bit different than the traditional definition of work, and it may actually be slightly different than what the book talks about with how to define work, because I think there's a little bit we could do it a little bit better way using a tiny little bit more mathematics. So the definition of work has 3 factors to. Let's see, we've got to have a brush here. All right. So the definition of work has 3 factors associated with it. So the work done depends on the force that is applied to the object to make it move, or that is at least acting on the object while it's moving. It depends on how far the object moves while that force is applied, and it depends on the direction between the force and the displacement, those 2 things. And that depends on a mathematical formula, trigonometric formula called the cosine. And it's abbreviated cos, and then theta is the angle. So the situation is like this. Let's say that there's a box right here, and you're going to push on the box. So let's say that you push on the box, or let's say you pull on the box. Yeah, that's even better. So let's say we've got a rope or something like that that's attached to this side of the box. Okay, and exert some force like this. So it's not exactly along the line of motion. Let's say the box is resting on a horizontal surface like this, and you're pulling it, not straight to the right, but with some angle upward and to the right. Okay, so as this happens, let's say that the box slides some distance d across the floor, so that I want to do that a little bit better. Maybe I'll try to represent this a little bit differently. So as the box moves, let's say that the box moves from this position here, and let's say that the new position of the box, which I'll put in as dashed, a dashed box. So that's the new later on position after it's had a chance to move a little bit. The box has moved to here, all the while you've been pulling upward on it with this force. Okay, so now I know that the box has moved. The front of the box went from there to there. So let's say that that's our distance d. That's what we're talking about. So the box is shifted position from from this leftmost position to the rightmost position under the influence of this force. Now, how much work was done by this force? It's what work really means is it's a way of measuring, assigning a number to the influence that the force has on the motion of the object. So, how much influence it has depends on, well, how much force you exert. The bigger the force, the more work you can do on the box. So that's one way to think about it. So if you pull really hard on the box, you're going to do a lot of work on the box. And if you pull really weak or something like that, then you don't do very much work on the box. Similarly, imagine that the work is kind of related to the effort you need to put in, but it's not the exact same thing. So there's a little bit of a distinction there between work and effort, but they're kind of sort of the same to an extent. The difference is that the physics definition of work actually requires that the object move for work to have been done on the object. In other words, it sort of demands results in a way. So to calculate the work done, it doesn't just depend on how hard you pull or how hard you push or the force that's exerted. It also depends on how far you move it. Now think about this for a second. Like, let's say you're doing a moving job or something like that, and you push a box across a room, and then let's say that you push that box across the room twice as far. If you pushed it with the same force but twice as far, you did double the amount of work. You pushed the twice that distance. So you get, the work done also depends on the distance that was traveled by the object while the force was acting. Now, this cosine of theta is actually sort of like an efficiency factor. And this angle then, in this case, you'll notice that the direction of motion is horizontal and the direction of the force is not exactly horizontal. There's an angle between those two. So I'm going to have it be a little bit smaller here so I can draw it a little easier. It won't look as good maybe, but there we go. It's not terrible. That's the angle theta. It's a Greek letter. And because we usually use that for angles and stuff like that. But the angle theta is the angle between the direction of the force and the direction of motion. The direction of motion is purely horizontal. The direction of the force is up and to the right. So the cosine factor is a factor. The function actually goes, depending on what the angle is, between positive 1 and negative 1. So just to give you a sense of this, if the cosine of 0 degrees, if that's our angle, then that's actually positive 1. The cosine of 90 degrees, so that's if the angle is a perpendicular angle, that's actually 0. And the cosine of 180 degrees, this is when the force and the direction of motion would be opposite of one another. That's negative 1. So those are the only 3 cosines that I'm going to really want you to know. Like I said, it kind of has to do with an efficiency factor. If the force and the direction of motion are in the same direction, then the angle that we would be talking about would be 0, and that force is being 100% efficient in producing motion in the direction that the object actually goes. If the force and the direction of motion are perpendicular to one another, that's 0% efficiency, really, because the force is not being at all efficient in producing the horizontal motion if the force is vertical. And similarly then, if the direction of motion is one way and the force is in the opposite direction, well then they're working against each other, and that gives the cosine of 180 is negative 1. So I get sort of negative efficiency there. It's not really an efficiency from the strictest sense of the word, but from a sort of a gut reaction sort of sense, I think hopefully it works and makes sense to you. So are there any questions so far on how these quantities, the force, the distance, and the cosine function, this angular function, which describes the efficiency of the force relative to the direction of motion, is there any question on how that all works together to produce this sense of what work in physics means? So I'll pause to sort of take questions on that. Any questions from the chat? If there are no questions, just say it's all good, or no questions, or it's clear, or whatever. But so far, no one said anything in the chat, and it says I've got viewers here, but I want to make sure that folks are paying attention or watching or something like that. Okay. Hi, Lauren. All right. So that gives the idea of what work in physics means. So that was sort of the basic idea of the first lecture, was defining that. The other thing that we talked about briefly then is the idea of power. Oh, we should talk about units. We'll talk briefly about units here to make sure that that's clear. So I'll erase my mark there. There we go. Okay. So units of this. The unit of force, like usual, is the unit of the Newton. The unit of the distance is the usual unit of the meter. So work then has sort of kind of basic units of newtons times meters, which we redefine the unit of newtons times meters is redefined as the joule. I know it's kind of it's capital J is the abbreviation for joule. I know it's spelled like jowls because this is what it looks like. It's joule is Joule. That is the pronounced joule though, just so folks know. So that's the unit of the joule. So this is the unit of work. So the definition of work is force times distance times cosine. The cosine is just a number, so it doesn't have any units associated with it. So all of the units are contained in the force and the distance. So that's that. There was another part of what we talked about of the idea of power. So let me sort of divide that off. The unit of the idea of power. Now power is the rate at which work is done. Okay? So let's say that you do some work and it takes you, moving some crates around a room or something like that. You're doing your moving job again. Let's say you do some amount of work by exerting force over distance, and then you time yourself. Well, how long does it take me to complete the job? Okay, well, that would give you the power then. The power in physics is the rate at which work is done. So you divide the total amount of work that was done, you divide it by the time that the work took to complete, and that'll tell you what the power is. The unit of the power, I'm going to put this in parentheses, I guess. It goes like units-wise, the unit of work would be joule. The unit of time, of course, is second. So a joule per second is defined as a watt, which that is a unit you might have heard about before. So a joule is not that popular in everyday language, but the watt is something you've probably heard of. So the thing that is a little bit confusing about this, and hopefully it won't be terrible, you'll be able to sort of distinguish it, but the abbreviation for the unit of the watt is capital W, which unfortunately is also the symbol that we use to represent work, which isn't surprising because work starts with a W. But hopefully you'll be able to distinguish that this W right here is the symbol for the work that is done, whereas if I was abbreviating the unit of the power, I would express it in watts. So hopefully that's not confusing, but keep in mind that to keep those things separate in your head at least. So that's the idea of power. So when you talk about where you may have heard about the idea of wattage or watts or something like that before is in, I'll say, light bulbs or something like that. The wattage of a light bulb is actually telling you, expressing to you how many joules per second are being consumed in electricity to make that light bulb go, to light up that light bulb. So a 60-watt light bulb is consuming 60 joules of electrical energy every second to produce the heat and light that the light bulb makes. A kilowatt is 1,000 watts, just like a kilometer is 1,000 meters. So a kilowatt is 1,000 joules of consumption per second. That's what a kilowatt would be. Now, the Old English unit of the power is the horsepower, and of course there's a conversion factor between the metric and the Old English units. And I think it's, if I remember from the lecture notes, I think it's like 746 watts is the same thing as 1 horsepower or something like that. It's a weird conversion factor like that. But notice that, your car's engine is measured in horsepower. Basically, that's how much energy per unit time the car could put out. It's not actually consumption, it's actually output for that one. And of course, you could express a car's horsepower of 200 horsepower. You could express it in watts. And in fact, if you have a European make car or a Japanese make car, something like that, if you check your owner's manual for your car, it would actually give the engine power. It probably gives it in horsepower too, because it's made for sale in the United States. But it probably also talks about the power of the engine in kilowatts. Okay, which may seem a little bit weird, but it's not. They're both units of either energy production or energy consumption. And the efficiency of something would be the power output divided by the power consumption rate. So a car might be, say, 20% efficient, which would mean that for every 100 joules per second it actually consumes, it's only putting out 20 joules per second of actual output, of actual physical work done. So there's some waste in there. So that's what efficiency really means, is the rate at which power is produced compared to how much is consumed. Okay, so are there any questions on the idea of the definition of work and the definition of power? Hopefully that's relatively clear. So I'll pause for that, and then I'll clear this out here, and hopefully we'll be able to clear this and clear this space. So we have some more space for questions and answers and stuff like that. I don't know where that came from. I'm erasing it. There we go. Okay. Any questions that I can answer about those definitions now? All right. So I'm going to move on. Again, if your questions show up after I start with a new material, no problem. I'll answer them as they come up and as I come to them, as I finish my thoughts on things. So, all right. Hey, Avery. Hey, Michael. So the idea then is work is related to this concept called energy. So we start with the definition. This is sort of going into the second lecture that was sort of for today. And we start with the basic idea of the energy associated with the motion of an object. So when an object moves, it has a property, a number that you can associate with, a property that you can call its energy. And the type of energy that it has is going to call it, we're going to call it kinetic energy. Kinetic basically always refers to motion. So like in kinematics, we talked about that kinematics from Unit 1 was the study of motion, has that word kena in it. So kinetics or kinetic energy is the type of energy it has because it's moving. So the kinetic energy, let's define energy as the number that you can assign to an object that allows it to do work. So let's talk about the kinetic energy of a hammer, okay, that you swing. Okay, so let's say that you wanted to pound a nail into a wall. Okay, now the way that you do that is, well, what you want to do, of course, is you want to do work on the nail by exerting a force over some distance to drive the nail into the wall. So there's the situation. Now, the instrument that you're going to use to drive the nail into the wall is the hammer. Okay, so you're going to give the hammer, by pushing on it with your hand and swinging it with your hand, you're going to give that hammer some kinetic energy, which allows it to do work on the nail to drive the nail in. And the kinetic energy that the hammer has is going to depend on the motion that you impart to the hammer by your pushing on it. Okay, so let's think about what about the hammer allows it to do lots of work on the nail? Well, let's think about that for a second. First of all, if you swing the hammer faster, when it hits the nail, it's probably going to drive the nail in further into the wall. In other words, it's going to do more work on the nail because it's moving quicker. So that's one property that the hammer has, at least momentarily, about its motion, that allows it to do work. The faster it goes, the more kinetic energy it has, the more ability to do work because it has motion that the hammer has. Then the other thing that is, so if you swing the hammer faster, it's going to drive the nail in further. So more speed means more work can get done, which means it must have more kinetic energy. But let's say that you swing the hammer, two different hammers. One hammer is really, really light, has a really small head on it or something like that, and you swing it with some speed with your arm. And then let's say they got a big old hammer head on it, way more mass, and you swing it at the exact same speed. I think it's pretty obvious that the more massive hammer, the heavier hammer, is probably going to be able to drive that nail in further if it's traveling at the same speed as the smaller hammer. So more mass means more kinetic energy for the same speed. So the formula then for the kinetic energy is going to have to involve those two quantities, the mass of the object which is moving and the speed that the object has. And it turns out that the formula, and I'm going to use capital K for the kinetic energy. I think the book uses like an abbreviation KE, and that's fine, whatever you want to use, but I don't like to use abbreviations in my formulas because I think the dots and the E's and the more than one letter symbol to represent something is usually a bad idea because there's the potential for it to get confusing. So my symbol, I'm just going to use capital K. So the formula for the kinetic energy ends up being 1/2 times the mass, so there's the part where it depends on the mass of the object that's doing the moving, times the speed squared. I know that's a V, but that's the magnitude of the velocity. So what we have here is a number. There isn't a direction associated with this. Here's a way to calculate a number. I know it's not the simplest formula that you can use, but it's one that ends up being consistent with the idea of work and energy and motion later on. So this is the idea of the kinetic energy. And notice it does depend on the two factors that we thought it would. It depends on the mass of the object. It depends on the speed of the object. It depends on the speed more, it turns out, because the speed ends up getting squared. But notice the kinetic energy, the smallest value of the kinetic energy that an object can have is 0. It can't ever be negative, because even if the velocity was negative, like you put in a negative number here for the velocity, when you square a negative number, it comes out positive again. So the only way that an object can have its smallest amount of kinetic energy is when it is at rest with velocity 0, and then the kinetic energy is 0. The mass of all objects is greater than 0. We have no negative masses, so the kinetic energy always has to be a positive number. Okay, now, hopefully that's okay and it's relatively clear. Now, how is work and kinetic energy related? Well, let's talk about the swing of that hammer. Let's say that, we're talking about, because we're going to use that hammer to drive in the nail. Okay, so if we do that now, the kinetic energy that the hammer gets because of your swing depends on the work that you do on the hammer. So here's the deal. The work and the kinetic energy are related in a lot of ways. And the way to express the relationship is if you do work, and here it's going to be the total work done by all the forces. If work gets done by a number of forces on an object, it turns out that is equal to, will always be equal to, the change in the kinetic energy of the object that the work was done upon. So the change in the kinetic energy, this is final kinetic energy minus initial kinetic energy. All right, so that's what we mean by that. So it's always, the change in the kinetic energy is always final minus initial. Okay, so what does this mean? I'll use sort of like hopefully a relatively concrete example. Let's say we're talking about that hammer again that we're going to use to pound in the nail. Okay, now when you start to swing the hammer, it starts with zero velocity, so it starts with no kinetic energy. Then you exert a force on the hammer to swing it. Now, if the force that you're exerting is the only force that acts on the hammer, then the total work done by all the forces is just the work that you do on the hammer. Now, what is the work that you do on the hammer? Well, you can calculate the force times the distance times the cosine of the angle between the direction of motion and the direction of the force, just like we were talking about earlier. So you calculate that work done. That is equal to now the change in the hammer's kinetic energy, and it started out with zero. So what happened is you did work on the hammer and you increased its kinetic energy from zero to some final value, which has to do with how fast it's going and how much mass it has. Okay, so now you've done some work on the hammer and the outcome is that it has some kinetic energy. Subsequently, that hammer, which has some kinetic energy, could exert a force on the nail to do work on the nail, and it brings the hammer to rest, and then it's given up all its kinetic energy to do work on the nail and drive the nail in. So basically, you've transferred work via the hammer to the nail. You've done work on the hammer to swing it. You've given it some kinetic energy, and then the hammer, when it hits the nail, gives up its kinetic energy to do work on the nail to drive it in. So that's sort of a process. And any object in general that takes one type of energy, like the energy that you had from swinging the hammer from your muscles and stuff like that, and transfers to another type of energy, any way of transferring that, we call it an engine. So in effect, if we want to be technical about it, that hammer is an engine that converts the energy that you have in your body to a new state of motion for the nail. So that's kind of, I guess, technical, but that's sort of a really simple it's a really simple engine, a really simple machine that lets you do that. Are there any questions on this? This idea right here, this is called the work energy theorem. It's the relationship between the work done on an object and its kinetic energy. So I'll pause that and ask for questions. And there haven't been any questions so far about it, either homework or anything like that. Have folks had a chance to look at it? Are folks wondering? I know right now I'm kind of dominating the conversation and telling you about stuff from our lectures, but I'm hoping that you've had a chance to look at them and you have some questions on how to move forward. So feel free to ask those now. I don't want to just get in the way and have my big talk happen here for an hour or whatever. I want you to tell me what you want to know. Are there any questions so far? Please ask them. I've got the book open in front of me, so if you've got questions on a particular exercise or something like that, I'm happy to answer them. Pop the book open to that spot and we can get her going. So while I'm talking here, I kind of want you to be thinking of questions or stuff that's related to what we're talking about or anything like that. Go ahead and ask. So I'm just waiting for questions to pop up. I know it's early. Here we are at 10 a.m., right? 10:30 now. So stop looking like a lot of questions are just piling up in the chat right now. So I'll talk a little bit more then about the idea of work and energy. And, okay, question 4 from homework 19. Let's see, question 4. Let me pull up. Okay, so we just had a question pop up in chat. Let me look at what question 4 is. From homework 19. Homework 19, question the 4th one. Oh, is it Q4? Let me look here. What do we got? I want to make sure I'm doing the right one. Okay, yeah, oh, Q4. All right, good. Okay, so Q4, first of all, it describes there's a situation for, that it's describing here. And basically, it's very similar to what I drew earlier. So let's draw what the situation is. It says we've got this, it's really similar to what I drew before. Okay, you got a horizontal surface and a box, and then there's a force acting on it at some angle, and then the box has shifted position by an amount d. So there it is, so it's gone a distance d under the influence of the force F. And the question is, question 4 asks, in the situation pictured in question 3, if there is a frictional force opposing the motion of the block, does this frictional force do work on the block? Okay, so this is sort of a definition sort of question. Okay, I am going to erase these ones up here. Hopefully that will. All right, give us a little bit of space. So remember, so when you're calculating the work, there could be work done. So this is what I'm going to write this down just so that it's clear what I'm talking about. This here, usually when I write down the work done, I use a little subscript here to indicate what work I am talking about. This would be the work done by force F. This would be the work done by gravity. This would be the work done by the force of friction, because usually I use a small f to indicate friction. Okay, so in this case, what I would do is I would say, well, the work done by the force F, well, that would be equal to F times D. And by F here, I don't mean a general force. I mean that specific force right there, times D, times the cosine of, and I guess I'll label this as theta F, which is so this is a subscript on the theta here, so I guess I'll put parentheses around that so that's clear. This is the theta that is associated with force F compared to the direction of motion, which is horizontal here. D is always the same. Okay? So this is the force, the angle, that the force F makes with respect to the horizontal. Now, what this is asking about, question 4 is asking about, is the work done by friction. So here, this would be, okay, it would be whatever the force of friction is, its magnitude, times D, times the cosine of the angle theta with a little f, the frictional force. So this is the angle that friction makes compared to the horizontally to the right, which is the direction that it's moving. Okay, so when that question is asking, in the situation pictured in question 3, if there's a frictional force opposing the motion of the block. Okay, so what do you suppose? If the motion of the block is horizontally here to the right, then you'll probably think to yourself, if I was going to draw a free body diagram like we kind of usually do for situations like this, the frictional force probably goes to the left. And I guess I'll put here, I'm going to put the direction here for D, just so that is also clear. Okay, so I'm not going to completely answer for you, but I think I've set you on a pretty good path here to answering the rest for yourself. Whenever you're calculating the work done by a particular force, it's that force multiplied by however far the object moved, times the cosine of the angle that that particular force makes with the direction of motion D. So then ask yourself, does friction do work on the block? And then explain. And by does it do work, it means, is there work done on the block that is different than 0? Okay, if the answer to that, if it's different than 0, then the answer is yes, work was done. Okay, hopefully that answers the question. Avery, can you let me know if that was clear, or if that maybe it's too much, but hopefully that clarifies things. There could also be work done. You could also have the work done by the normal force here. So I would label that W sub n, where then got a normal force acting on the block. And while I wait to see if this was good enough, if that answers the question. Okay, good. Avery says that answers it. The other, you will notice in one of the things I just erased was the idea that the total work done. That's another subscript that I use sometimes when I'm talking about the work. The total work done is the work done by all the forces put together. To calculate that, if all the forces that act on that block in that picture are F, gravity, friction, the normal force, if that's it, if that's all the forces, then the total work done would simply be the sum of the work done by all of the individual forces. Work done by gravity, and then there's more of them. I just ran out of space here, but there's a second line here that we have to continue adding. Then there's the first force of friction could do work. And then there'd be the work done by the normal force too, which, some of these might be 0, some of them might be positive, some of them might be negative, but when they add all up, you get the total work done. Okay, so that's the way that you calculate the total work done by all the forces together acting on the object. And notice that the D in this is the same. The object moves however far it moves. So the D is the same for each one of these. It's the F that's different and the theta that might be different if the forces are in different directions compared to the direction of motion. Okay, so I'll pause again and see if there are any other questions. Like I said, you don't have to wait for me to stop talking on something to ask questions. Just ask the question in the chat as it comes, and I'll just go with the flow. Okay, so any other questions? All right. Well, it doesn't seem like there's a lot more questions popping up. So I've kind of gone over the basics of what we did for the lecture that was posted for Monday and the lecture that was posted for today. I guess I'm going to transition in just a moment to the lecture notes that we're talking about for Friday, which is the idea of potential energy and the idea of conservation of energy. So just one moment. I'm going to do one thing before I'll be off camera for just a second, but I'll be right back. Sorry, if you weren't distracted, I was slightly. So anyway, so looks like another question popped up. So the second multiple choice question for the lecture for today. All right, so this is out of the lecture. Let's have a look at that. I'll pull up the lecture notes for today and see our second question for lecture notes for today. So the multiple choice. Yeah, that one's a little tricky. So that multiple choice question, so I'll read it so folks have an idea. So it says we have got a block lying on a frictionless horizontal surface. So no friction to worry about. It says a constant force is exerted on this block and it accelerates to some final speed after traveling a certain distance. If this same force is exerted on a block that has double the mass, but over the same distance, how does its final kinetic energy compare to the lighter block? That's what we're being asked about. So let's sort of draw it to give you a picture. I'm going to clear things out here so that we can see a little bit better. All right, so the situation is kind of this so that we can see. Let's say I've got a block and it's sitting on a horizontal surface. So here's a really little block. Again, it's going to be sitting on a nice, whoops, there we go. Imagine something like that. This is a frictionless surface, and you pull it with a force F, and it finishes over here, again, some distance away after you continually pushed on it. It finishes after traveling some distance d to the right. Okay, and it asks about the final kinetic energy of this block. Let's say that it started from rest, and we want to know how, it has this final kinetic energy. I guess I'm going to get rid of this. All right, so there's the final kinetic energy that it has. It starts out with no kinetic energy because it starts out at rest. Okay, the second, so it says, all right, it's got some final kinetic energy after you exert some force over some distance. And then the second situation is, all right, well, I've got this horizontal surface, but now I'm going to take a block that's twice as big. I'm going to exert the same force on it. So this is the same magnitude for the force. And now this block is going to travel. This block, oops, I was making these dashed, wasn't I? All right, well, no big deal. All right, there we go. We're making these dashed for what they look like later. So the block has moved, this bigger block has also moved a distance d. And we want to know how its final kinetic energy compares to this one. Is it bigger, smaller, 4 times as big, double? Is it the same? Hard to know. Okay. So I've got this bigger mass block, and if you wanted to solve this problem using kinematics and Newton's laws, it would be kind of complicated, but the work energy theorem actually makes it easier. In both cases, this expression, this total work done on the block, is equal to the change in its kinetic energy. Okay, which is, the change in kinetic energy is always final kinetic energy minus initial kinetic energy. Now, if each of the blocks start out at rest, so this block starts out at rest, and this block starts out at rest, the kinetic energy of this block when it starts out was 0. Okay, and then the work done on this block is what produced its final kinetic energy. So the work done on the block is equal to its final kinetic energy because it's equal to the change. The change, it was from 0 to whatever its final kinetic energy is. All right, so then, now if I have a bigger block, I exert the same force over the exact same distance. Notice that that's the same amount of work. No matter how heavy the block is, how massive the block is, it's the same amount of work done because you exerted the same force over the same distance. So what does that mean? If the work energy theorem is true, that means they have the same kinetic energy. So the answer to that one is they have the exact same kinetic energy, which in the notes is number 3, answer 3. The heavier block has the same kinetic energy at the end as the lighter block did. Now, what's different? If they have the same kinetic energy, what's going on is if this block is less massive, the top block is then it's actually going to be going faster. It travels faster. This one doesn't travel as fast, but it's the work energy theorem tells us that they'll have the same kinetic energy even though this one's traveling slower, this one's traveling faster. This one has more mass, this one has more speed. So they're 1/2 mv squareds. If you would calculate those each individually, they turn out to be exactly the same. Okay, does that answer the question? I'll pause and see if folks are okay with that. You can have a follow-up if you want, if there's something that I said up here that wasn't clear. right. Doesn't seem like there's a lot of questions popping up again. Okay, good. I'm glad it makes more sense. Okay, so I guess I will clear this out so we have a little bit more space to work with. So, we've been talking about the idea of kinetic energy and work. Those have been our main concepts for Monday and Wednesday. Give you a little bit of prelude then to what we're going to be looking at Friday if you haven't had a chance to look at those yet. Okay, so Mike just popped up now. Michael asked a question, what would be the answer to question 1 with the marble, because they would have the same speed? Yeah, that's a good point. So that the question he's referring to with the first question says we have 2 marbles, one marble's twice as heavy as the other, are both dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has, and then there's a bunch of things, comparing. It has twice as much kinetic energy, 4 times as much, half as much kinetic energy as the lighter marble, or the same kinetic energy as the lighter marble. The answer here is that they have, it has twice as much. The heavier marble has twice as much kinetic energy. They do have the same speed, you're right, but if I was going to use the formula for kinetic energy, in this case, 1/2 times mv squared, they both have the same speed when they hit. We know that from our work like 2 units ago back in Unit 1, where if you drop 2 marbles and you can ignore wind resistance, they hit the ground with the same speed. Okay, we got that. So I hit the ground with the same speed. So the V is the same for both. The thing is, the heavier marble has twice as much mass. So the V squareds are the same, but when I multiply it by a mass that's twice as big, I get twice as much kinetic energy. So from the definition of kinetic energy, that sort of hopefully makes sense, that it depends not only on the speed, but it also depends on the mass. Okay, so that's sort of an alternative. So the idea that we would be getting to on Friday then is the idea of conservation of overall energy and the idea of potential energy. So the first idea is the idea of potential energy. So I'll discuss while I wait for a question. You're welcome, Michael. The first one I'll discuss then is the question of the idea of potential energy. And let's return to the idea of pounding in the nail or pounding in a tent stake. Okay, so let's talk about that, because I think that's a useful analogy to use and one that I've typically used in class before. So when we were driving in the nail with the hammer, we said that the kinetic energy that the hammer had is capable of doing work on the nail by driving it in. And the more mass it has and the more speed it has, the more work it could do. So the more kinetic energy it must have. But there's also the idea of potential energy, which is energy of position. So you can say those two go together because they both start with P. Positional energy and potential energy kind of go together. So this is positional energy in a force field. So what I want you to think about is, let's say I've got this rock because we forgot our hammer at home and we still have to drive in tent stakes because we went camping. Okay, so let's say you go around, you find this rock, and you take the rock and you hold it above the tent stake and you just drop it. Instead of like using it like a hammer, you just drop it because you're tired, you don't want to use it. So you lift it up there and you just drop it on the tent stake, and it drives the tent stake in. Now, if you pick up the same rock and you lift it, so it did some work on the stake now, because the stake gets driven in some distance because some force was exerted on it. Now, if I lift the rock up higher above my head and I drop it on the tent stake again, the work that's going to get done from dropping it from a higher height is going to be bigger. So that must mean that there's some sort of energy which depends on the height that the rock has. So the energy that the rock has must be bigger at larger heights. And the reason why it has more energy is because the force of gravity is acting on it. So we're going to call this the gravitational energy of position, or the gravitational potential energy. So the higher the rock goes, the greater its gravitational potential energy, because it has more possibility or potential to do work driving in the stake, the higher it is. Now, what if originally you had your little rock like this big or something like that, you dropped it from some height, and it did some work to drive the stake in. Let's say that instead I decided I don't want to use that little rock anymore because it's not working very well. I'm going to go grab a big rock, way heavier, much more weight to the rock, more gravitational force that's exerted on it. And let's say that I take this big rock now, that weighs more, and I drop it from the same height as I dropped the original rock. The stake's going to get driven in way further because because it's heavier. So the gravitational potential energy must depend on two properties of the rock. It must depend on the weight of the rock, and it must depend on the height of the rock, because the higher the rock goes, the more work it could do too. So it depends on those two things. So the gravitational potential energy formula has to depend on the weight of the object and its height above some reference point. So I'm going to use U, the letter U, to represent the gravitational potential energy. In the book, they might use like GPE or PE for potential energy, or GPE for gravitational potential energy. I'm going to use the symbol U. It's kind of standard in most textbooks to use U, so I'm going to use it. So hopefully you can make that sort of translation. So this depends on those two properties that we talked about. The weight of the object, so this is calculated as m times g, so you take the mass times the gravitational constant, and then the height that the rock has above the ground or above the reference point. So I'm going to call that y, the vertical position of the rock. Now notice that this value of y depends on what you decided your origin, what you decided y equals 0 was going to be. So you're actually free to choose. When you start a problem, you're free to choose any height that you want as your reference height. So for instance, let's say, here I am, I'm in my basement right now, but my wife's right upstairs, and she might be like holding onto her coffee cup or something like that up there, and she says, I'm going to use the floor of the first floor, the ground floor upstairs, as my reference height. So my coffee mug is my wife's coffee mug might be, some height above the floor upstairs. So she could use that as y equals 0, and then the height could be 1 or 2 meters or whatever that is above that. Me, if I was doing physics problems in my house, I would be using the basement, because that's where I'm sitting right now. So I would use the basement as my y equals 0. So we would disagree on what the gravitational potential energy would be. But notice, if my wife's coffee cup came downstairs, then relative to the floor up there, her y values would be negative. So she would get negative values of the gravitational potential energy, whereas I would still have positive ones. So we disagree on what it is. But notice that when we're talking about how much work can get done by the coffee cup as it moves between two heights, only differences in potential energy can possibly make any difference in physics, can possibly be concerning to us in physics if we're going to do a calculation. So it doesn't actually matter which height you use. You don't have to agree on what the gravitational potential energy is. You just have to tell me what you're using for y equals 0. You could use the floor upstairs, you could use the floor in the basement, or you could use the floor on the second floor, and all these other values down here could be negative. It doesn't matter as long as you're clear. And as long as you don't change what your reference height is in the middle of the problem. Once you've chosen your reference height in the beginning of the problem, stick with it through the end of the problem and don't change. That way you won't confuse yourself by trying to compare potential energies from different parts of the problem using different y equals 0s. Okay? So usually we just make it easy and say it's the ground level or it's the floor level that you're currently on or something like that. That's where y equals 0 is, and then your gravitational potential energy is measured relative to that. It could be positive, or if you go below that y equals 0 spot, could go negative on you. But it doesn't matter, just keep track of it. Positive or negative doesn't matter. If you get a negative number, no problem. You can have negative values of gravitational potential energy. Okay, so this is the gravitational potential energy. I'll put a little g next to that to indicate that this is for gravity. There's another type of potential energy that we can use to solve problems as well, and that is the potential energy associated with the force exerted by a spring. Okay? So the thing about a spring that's different than just gravity, for instance, is notice that the gravitational force that's exerted on an object at different heights is the same. Doesn't matter how high you are, basically, as long as you stay close to the surface of the Earth, the weight of the object doesn't change. Not really, anyway. We know from Newton's universal law of gravitation that if you get really high above the Earth, that the weight can change, gravitational force can change. But let's say we're staying close to the surface of the Earth. If I'm talking about a string that is stretching horizontally, a spring that is stretching horizontally, I know that if I stretch the spring more, the spring exerts a bigger force. And it turns out that for most springs, the force is linear. If I stretch it by 1 meter, maybe it's 1 Newton. If I stretch it by 2 meters, the force it would exert is maybe 2 Newtons. It's linear in the amount of stretch. So the work that you do in stretching or compressing a spring is dependent on how far it gets stretched and also how stiff the spring is. So it turns out that the way to determine what the elastic potential energy is, it's associated with a certain amount of stretch, is the following. I'm going to call this the elastic potential. That's supposed to be an E. Imagine that that's a really good E. It's not, but imagine it is. The elastic potential energy, the amount of energy that a mass and spring can do, is equal to 1/2 times, and this is a small k, not capital K, but small k, times x squared. Okay. Now, what do these symbols mean here for the elastic potential energy? We'll start with the idea of K. This little k here, this is not kinetic energy. This is capital K, this is a little k. The little k here is what we call the spring constant. It basically characterizes how stiff the spring is. So a stiff spring would have a very high spring constant, which is measured in newtons per meter. So I'll put that there in the units of this. There's newtons per meter. So that means how many newtons of force do I get with a certain number of meters of stretch? So a spring constant of 1 Newton per meter corresponds to a string that if I stretch it 1 meter, I get 1 Newton. If I stretch it 2 meters, I get 2 newtons. If I stretch it 3 meters, I get 3 newtons of restoring force exerted by the spring. Now, if I had, let's say, a spring constant of 12 newtons per meter, then that would mean if I stretch it by 1 meter, 12 newtons of compression force are being exerted. And if I stretch it to 2 meters, I get 24 newtons of restoring force back to the original spot. So it tells you how stiff the spring is, how much force does it exert compared to how far you stretch it. The more stretch, you always get more force, but the stiffer the spring, the more force you get per each meter of stretch. Okay, so that's what little k means, the spring constant means. This x is how far have you stretched or compressed the spring. If you stretch the spring, how much? So every spring has its own natural length, which we call its equilibrium length. So if you just let it alone, the spring will just sit there and have that particular length. Now, if you stretch the spring, x is a positive number. I've made the spring longer than its equilibrium length, and x tells you how much you've stretched it by. Okay, so that's sort of the dynamical part of it. The thing is, if your spring, which has these separated coils, you could also compress it, making it shorter than its equilibrium length. Now, if you do that, x is negative. But notice that by compressing the spring, you also increase the elastic potential energy stored in the spring. It wants to get further apart. It wants to spring back to its original length. And even if x is a negative number, because it gets squared here, you'd store the same amount of elastic potential energy stretching a spring by some amount x as compressing it by that same amount x. So this is the amount of stretch or compression. So that's what x means. It's the amount of stretch of the spring from equilibrium, from its equilibrium length, or, there's also compressing. Okay, so I'm kind of writing this so that you have a chance to ask questions while I am doing that. So is that clear? So this then is the amount of work that a mass that is attached to a spring could do. If you stretch it by some amount and you let it go, the spring will move because of work done by the spring, changing this elastic potential energy into kinetic energy. Okay, any question on those ideas? We're sitting at an hour right now, and I was going to go, I know, at least this long, but I want to make sure your questions get answered first. Okay, any questions on this idea of potential energy? We have two versions. We have gravitational potential energy, and we have elastic or stretching potential energy from the spring. I'm going to kind of go on to talk about this now, but please ask questions on how this works. Okay, Lauren says none. Okay, good. So here's sort of the final idea that I want to get across, and it's a really profound idea, it turns out, because it allows us to solve problems in physics that would be really hard to solve if we were just going to use Newton's laws. It would require, if we're going to solve these style of problems using Newton's laws, we'd have to use calculus to do it. Okay? So it would be that difficult. Okay, so the idea then is the following. The total mechanical energy of a system, I'm going to call that capital E, can be written as the sum of the kinetic energy plus all of the potential energies of a system. This is the total mechanical energy is equal to the sum of the kinetic plus the potential. Okay, so now let's think about what happens. The total mechanical energy of a system remains a constant as long as no energy or work is done on the system or there are no forces that spill energy out of the system. So let's say that I have what we call conservative forces, forces like gravity, forces like the spring, and those are the only forces that do work on the system. If that is true, then this quantity, this sum of the kinetic plus the potential energies, remains constant. So let's talk about that idea briefly and then ask questions as they come to you here. Let's say that I start out and I have a ball, and let's say that I have the ball exactly on the floor, way down on the floor here, okay? So I'm going to say y is equal to 0 at the floor. And I'm holding on to the ball, and I throw it upward. Okay, so the ball is moving upward. It starts at y equals 0, and I give it some velocity upward with my hand by doing some work on it because I exerted a force on the ball. Okay, after I'm no longer touching the ball, at the moment when it leaves my hand, it's still at y equals 0. It doesn't have any gravitational potential energy, but it has kinetic energy because I gave it some speed. So now what happens? The kinetic energy is traveling upward. The kinetic energy is positive as it's going upward. But what happens as it does so? As it goes, as it moves upward? Well, the gravitational potential energy as the ball travels upward increases. In order for the sum to stay the same, though, what has to happen to the kinetic energy? So if the potential energy starts out here and the kinetic energy starts out up here, so this is kind of like I'm graphing them. Okay, there's 0 potential energy to start, and now I've started out with kinetic energy. As the ball rises, the potential energy increases, but the potential energy goes down so that the sum stays the same. And notice what it does. It's trading in this case. The total mechanical energy stays the same, the sum stays the same, but as the ball travels upward, the potential energy goes up, the kinetic energy goes down, and eventually you go to a spot where all the kinetic energy is gone. It's been transferred into potential energy. So now I've got gravitational potential energy. I've got this height where it's reached its maximum height, the highest that it can, the highest height that it can go. And the reason it can go that high is because it had enough energy to get to mgy equaling what the original kinetic energy was. And now it's run out of kinetic energy, and all of my energy is now on the kinetic energy side of things. But then what happens next? The ball begins to fall back down. It's not at velocity 0 after it starts to fall back down. The kinetic energy starts to go up. The ball starts to fall, which means it loses gravitational potential energy. Eventually you get to the point where it reaches the floor again. The kinetic energy is back to where it started, and the gravitational potential energy is back down to 0. And that's the situation where you can think of how the ball moves in terms of energy rather than in terms of forces and kinematics. So this is an alternative way of looking at how objects move. The idea of conservation of kinetic energy. Conservation of total energy, with it being the sum of kinetic plus potential. Okay, now, I see that there's a question in there, and I'm going to finish my thought, and then I'm going to get to SP1 as you asked. Okay, so now, what happens if, instead of just gravity acting, what if I also have wind resistance? Wind resistance is one of those forces that actually does negative work on the ball as it travels. No matter if it's going up or it's going down, it does negative work because the force of wind resistance is always opposite the direction of motion. So the cosine of 180, no matter which way it's traveling, it's always a cosine of 180. It always gives you negative work done. So it actually steals energy out of the system. So what happens then is, if you include wind resistance, the ball doesn't go as high, and when it gets down to the ground, it's got less kinetic energy than it started with because some of that energy has been stolen out by wind resistance, which kind of acts like friction. Friction is another example of a force that steals energy out of the system. These are called non-conservative forces, forces which don't conserve total mechanical energy then. Okay. So hopefully that's clear. Go ahead and ask questions on that. I want to get to this question on SP1, or question 3 in the second homework. So SP1. So I'm going to erase these things so I can look at SP1 and give you a look at that. So SP1 from chapter 6. Okay. So SP1 asks the following. It says, suppose that two horizontal forces are acting upon a 0.38 kilogram wooden block as it moves across a laboratory scale. The two forces, it then details. There's a 6 Newton force pulling the block and a 2 Newton frictional force opposing the motion. It then says the block moves a distance of 1.7 meters across the table. So then the questions then are, part A is, what is the work done by the 6 Newton force? B, what is the work done by the net force acting upon the block? C, which of these two values should use to find the increase in kinetic energy of the block, so on and so forth. So I'm going to give you some ideas about how to look at this. So there's our horizontal, here's our block. There's a 6 Newton, I'm going to call it capital F. There's our 6 Newton force. And then it said there's a 2 Newton frictional force this way. I don't know if this is exactly to scale, but this is friction. Oops, there should be an equal sign there. There we go. All right, 2 Newton. All right. This one, forces to the left, has a magnitude of 2 Newtons. Okay. So those are the two forces that it lists. And then it asks, okay, what is the work done by the 6 Newton force? Okay, so that's what I labeled capital F. So you would use, no, we could kind of use this up here if we wanted. Maybe a good reason to save these things, huh? Okay. What it's asking then is, what is the work done by the 6 Newton force, which I labeled capital F? This is the frictional force. Okay, so now, what would you do here? I'm giving you a little bit of a hint. You can plug in the numbers. But remember how we talked about this. The work done by force F will be equal to the magnitude of F times the distance that the object moved, which it gives that there, and then times the cosine of the angle associated with force F. Okay, so what is the let's just, I suppose I should sort of draw this, make sure the drawing is complete here. The block moves to a new position, which I'm labeling as this dash position, which is a distance d to the right, which they give as 1.7 meters. Okay, so I'll let you from here decide kind of how to solve this. To calculate the work done by force F, you're going to look at the force F itself. What is the angle that force F makes with the direction of motion? The only cosines I am ever going to ask you for to actually calculate are cosine of 0, cosine of 90 degrees, and cosine of 180 degrees. Okay, so Avery asks, how do you know which angle measurement to use for theta? It depends on which which force I'm using to calculate the work. Okay, so for force F, it would be the angle that F makes with the direction of motion, which I think you can probably see. I don't want to give too much away here, but I'm gonna, because that's the first part. You can do the other parts, but the force F makes a 0 degree angle there in the exact same direction as the direction of motion. So it would be 0 degrees for that one. The cosine of 0 is 1, positive 1, as we mentioned. Okay, now, so maybe this is what Avery is getting to for the second part of the question. It says, what is the work done by the net force acting on the block? Okay, so I'll just I'll write this as the work done by the net force, which actually it turns out this is the same as the work done by the total work done. It turns out. Okay, so what this would be is unfortunately I'm going to have to use something for so I'm going to say the work done by the net force would be equal to, well, the net force, whatever the net force is, times d times the cosine of the angle that the net force, I'm going to put net there, but I should probably put, F sub n. But, okay, so the second part of the problem is, okay, so first of all, you have to figure out what the net force is here. That's going to take into account both of these. Okay, now you're going to have to decide what's the direction of the net force here. Right, left, up, down, up and to the right, down and to the left. I don't know, whatever. You figure it out. What is the direction? What is the net force? And there's going to be a direction for that net force. I don't think it's too much of a mystery, but I'm not going to give it away because I want you to have some fun with this. Okay, so this theta net then would be, what's the direction that the net force makes with respect to the direction of motion, which way is d. Okay, so d is directly to the right. Which way is the net force? What is the angle that the net force makes with respect to the right? Okay, does that answer your question about SP1 and Avery? I'm not sure who missed your mark is, but I'm going to call you Mark because I think you're probably Mark. Okay, so I'm going to kind of go on to the other parts then to give hints on those other parts, but hopefully that made sense. C, I mean that's a okay, good. I'm glad that was useful, Avery. C asks, which of these two values should you use to find the increase in kinetic energy? Okay, so I will let you know. Remember, what is the work energy theorem? We've written this down before, but the work energy theorem, in order to calculate the change in kinetic energy, it's the total work done is equal to the change in kinetic energy. If you want to know what delta K is, it's the total work done. So which of the two values do you think here corresponds to that? Okay. And then it asks about what happens to the energy added to the system via the work done by the 6 Newton force. Okay, so I want you to think about that a little bit. So does, and you're going to see how the work done by the net force and the total work done are related. Remember that the total work done gives you a change in kinetic energy. Where did the rest go? There might be a difference in the work done by force F, the 6 Newton force, and the total work done. The total work done, I know that produces a change in kinetic energy, but that might not be equal to the work done just by F by itself. So what happened? Why is there a discrepancy? What does that mean? And what I want you to think about is, what does friction do? Like if I rub my hands together, something like that, what do you feel on the surface of your hands? Think about that for a little bit. We don't have a way of accounting for the energy that's associated with heat yet. That's actually the second half of this unit. But in this part of the unit, we don't have a way of accounting for the thermal energy associated with heat and temperature. That's coming later. Okay. So, and then part E is using the definition of kinetic energy to kind of find out how fast the object is going. Remember that, K is equal to 1/2 mv squared. So hopefully that clarifies SP1. Remember that in a lot of ways, conservation of energy principles are like accounting. You got to keep different sides of your ledger. When you're dealing with work and energy, here's the ledger where I've got an account that has to do with the work done by force F. And then there's another account, which is the frictional account, how much work is done by friction. And then there's another account where there's work maybe done by gravity, or maybe there's work done by normal force. So you've got all these different accounts that you're keeping straight, calculating how much work is done by each. And then the total work done would just be the sum of all of those. So that would be the total sum of all of the value of all the different accounts. When you're doing this for conservation of energy, you only have really two sides of the ledger. You've got kinetic energy and you've got potential energy. And the two have to sum equal to one another, but as the object moves and changes its position and changes its speed, the kinetic energy may change and the potential energy may individually change, but the total should stay the same. And that's the idea of conservation of energy, conservation of overall mechanical energy of the system. The individual accounts for kinetic and potential energy might change, but the sum has to stay the same. Any other questions that I can answer for you? I know we're at an hour and 20 right now, but I want to make sure that all of your questions are answered. And I did check; there weren't any questions in the on the discussion boards that folks that weren't going to be able to be here wanted to see answers to. But I'm going to pause right here and see if there are any further questions, because I want to make sure these get answered before we call it for the day. So if you don't have any more questions, just say no more questions, I guess. But okay, folks are getting it. Hopefully this isn't too bad. I'll sort of sum up and keep an eye on the chat here to see if there are any further questions as I sum up. But so what we're doing with this chapter and this unit overall is this chapter of this unit is about an alternative way to figure out how objects move. The first way that we figured out how objects move was to use Newton's laws and forces to calculate their accelerations and things like that. And that was the subject of Unit 2. This is Unit 3 now, and we're talking about the alternative way to figure out how objects move. The bridge between what we did before and what we're doing now is the idea of work, which relates force to energy. Okay, because the definition of work involves forces and objects moving and that sort of stuff. Energy is a little bit more theoretical, I guess I would say. It's a little bit more abstract way of thinking, but it's just as good to figure out how objects move. Remember when we were talking about, the ball moves up and the ball falls down. I was describing how energy uses that to figure out how the object moves. It's an alternative way of thinking about how the object moves. We had a notion about how the ball travels up and travels down because of the idea of the gravitational force producing a uniform acceleration and so on and so forth. This says, yes, but another way to think about it is it has kinetic energy to start, and it trades that kinetic energy in for gravitational potential energy, slowing down, eventually reaching the top of its motion, and then falling back down, losing potential energy and gaining kinetic energy in the process. So it's an alternative way of thinking about stuff. Why do we want an alternative way to think about stuff? A couple of reasons. One is the mathematics associated with some classes of problems, like masses on springs, is really hard to do if you use Newton's laws, but it's really no more difficult to do using work and energy as other techniques. So that's valuable. It's useful. It allows us to do more problems, do more styles of problems, and learn how they move. The other thing that it is going to allow us to do is take a step into a new direction and talk about thermal physics and thermal ideas of energy, heat, temperature. That's the second half. That's the next chapter which is coming up. Okay? So we've got right now we got 1 foot in regular old mechanical motion, an alternative way of looking at it, and then we're going to step into some really new stuff in the second half of this unit when we talk about heat and energy and thermodynamics and the study of temperature. Okay, so I see folks are saying they don't have any more questions, so I'm going to thank you for your attention today. Thank you for your all the work that you've been doing online. I know this is not necessarily what you signed up for with this class, but I'm glad we're making some progress with it, and I'm really pleased with how it's been going so far. Like I said, I'll get the exams up, the exams graded by later in the week, and you should have some sense about what those were. By the way, I also wanted to mention that the whatever automatic grades that may have been posted, for the grades, it hasn't been downloaded to your exam 2, of course, yet. But any grades that you might have seen at the end of that, don't worry about that. Obviously, I haven't had a chance to, it can't automatically grade the problems. So anything that you saw there, don't worry about it. It's completely false what the score would have been. So also, if there were any problems that you experienced while doing the exam, or things that you think I ought to know about how the exam went, as far as the technical aspect of it, please let me know on the discussion board about that, because I want to fix any problems that might have arisen on the exam with your taking it. So again, I guess I'll end on that note. Again, thanks for your attention, and I will see you next week for our next live stream. All right. Have a great day. Hope you're all staying safe and healthy. Be well. Goodbye for now.